Thank you very much for your introduction. So my name is Zhe Shu from Hahn-Schickard Institute in Freiburg in Germany. So today I try to give you a short overview about our recent development using hybrid 3D printing for rapid prototyping by combining conductive metal and dielectric polymers for sustainable and smart 3D electronics. And here, just to give you a short, examples that currently in the consumer electronics, you can make really nice electronics, but you need a lot of process, like injection moldings. You need a lot of process to make the conductive PCBs, and then you need to do assemblies to make the product. It works quite well for the established product. It's quite reliable. But if you want to do the new generations, you need to implement new changes there. Then it's quite high cost for the prototyping, and also quite high cost for customized small series productions as well, and long design to product cycles. And also you have to share your designs, your IPs with your manufacturer so they can produce them for you. And what we are trying to propose here, that we try to think about, maybe we can use the additive manufacturing, hybrid 3D printing, to combine producing the polymers and the conductive traces, and make one hybrid design, 3D design, where we can process with a computer to generate G code, so CAM, and then with a hybrid 3D printer, we can print both materials layer by layer, and in between pick and place the components, so you have hybrid 3D electronics. Here we use slightly different approach. For general people knows this printed electronics. We have our own technology called StarJet, molten metal printing, which I will refer to it later. But let's first go to the polymer side. So we pick the FDM, so fused filament fabrication methods, to start. So we start with the low-cost pulsar system. We integrate our StarJet printhead next to it, so we can do layer-by-layer printing. And then we move along a little bit to improve the performance, to get a little bit high-end 3D printers, integrate different camera systems, so we can do better, more precise products. Of course, probably you also heard over the days that people has problems with polymers because you want to get injection molding grade of polymers. You need fair flame retard polymer. So that's why we are collaborating with Arborg. Arborg is a world-leading suppliers for the injection molding, and they produce their own 3D printers where they can produce, or let's say 3D printing injection moldable polymers in 3D. So that's very good. So we can also use the printers to, for example, printing fair retard linones. We can print PEEK, we can print PEI, so we can really high performance polymer there, and that will be our next step. So, and of course, for that one, what we are trying to do, we are trying also in the meantime try to streamline the process of from the design to the product and show how straight and relatively simple process. So you can make 3D design, you can export your the PCB design from the Gerber to the STL, and then combine with your 3D mechanics 3D design. So you have hybrid multi-layer 3D electronics design. Then with this design, you can load to the slicer, where in the slicer you can assign different materials to different extruders or print head. For example, here you can have yellow for the polymers, then you have pink for the metals, then the printers, if you load into the printer, you can print both material layer by layer on demand. And afterwards, you can have hybrid free-form 3D structures with embedded circuit and the components. And of course, we want to minimum the process as much as we can. So after you plug into the USBs, it's just a simple demonstrator that we can have a functional circuit right away. And now let's go a little deep into the technology background, why we choose direct molten metal printing for conductive traces instead of typical ink-based printing methods.